Okay, so let us start today's discussion with two linear operators. Let T and S be two linear operators on V, where S is non-singular, or that means regular. T may or may not be regular, but S is regular. Then S inverse exists, so we can consider this product ST S inverse. Now let us see what the square of this product is. By definition, this is just ST S inverse, ST S inverse, because S inverse S is the identity operator which will get vanished here, so we will have ST square S inverse. Similarly, the cube of ST S inverse turns out to be equal to ST cube S inverse, and one can continue like this. In general, we have this. For any natural number I, for any positive integer I, that means. This means if Qx is any polynomial over f, then Q of ST S inverse is equal to S Q of T S inverse. It may be a little difficult to see at once why this is the case, but let us just take a concrete polynomial and see how that is true. Suppose that Q of x is x cube minus 3x square plus 2. Suppose, then what is Q of ST S inverse? Simply replacing S with ST S inverse in the polynomial gives us this. ST S inverse cube minus 3ST S inverse square plus 2i. I mean, we of course have been writing 1 to denote the identity operator. Here, however, if you just simply write 1, it will look like 21. So I have decided to write I. Now, using these relations, we see that this is ST cube S inverse minus 3 ST square S inverse plus 2i. Now, in place of I, you can also write SI S inverse, because that ultimately is going to be I. And using the fact that we are in this algebra and we have the algebra axioms, this thing is equal to S times T cube minus 3t square plus 2i S inverse. That is using the distributive laws and the other axioms. And this is nothing but this. So that's how for this particular polynomial we are having this, but in general also you can understand that if you write a general polynomial here and do all the relevant calculations, then you are going to get this. Okay, so that's how we have this. In particular, it may happen that Qx is an annihilating polynomial for the operator t. In other words, Q of t is the zero operator. That's what we mean when we say that Q is an annihilating polynomial. It annihilates the operator t, it makes it zero. If Qt is the zero operator, then this is also the zero operator because of this relation. So the minimal polynomial Px of t is also going to be the minimal polynomial of ST S inverse. And this observation is a lemma. Let us first write the statement of the lemma. I mean, we have already written it here, but formally it's also given as lemma. And we will then see exactly how that is true. Okay, because it follows almost immediately from this fact, but still we need to see exactly how that is following from this fact. So we thus have the following lemma. So this is lemma 622, and it just states this, that both t and ST S inverse have the same minimal polynomial. If S and T are linear operators on V and S is regular, then T and ST S inverse have the same minimal polynomial. Let us write a proof of this. In the proof, we are going to simply write the main steps. Suppose Px is the minimal polynomial of t. Okay, so we are not formally writing anything, we are just simply going to see how the proof follows. So Px is the minimal polynomial of t. Then, in particular, this means that P of t is equal to 0. Hence, by the above observation, P of ST S inverse is also going to be 0. P of ST S inverse is also equal to 0. Okay, now fine. If you put the, if you evaluate this polynomial at ST S inverse, you are getting 0. But is it a polynomial of lowest possibility degree for which this is happening? That we don't know yet. So suppose there exists a non-trivial polynomial Rx in Fx such that R of ST S inverse is also equal to 0 and degree of Rx is less than the degree of, we are denoting it by P, okay, so degree of Px. And by non-trivial, of course, we mean a non-zero polynomial. So that means we have actually supposed that this is not the minimal polynomial of STS inverse, that there are annihilating polynomials whose degrees are less than even the degree of Px for the operator STS inverse. If we suppose so, then what is the consequence? Then using the fact that S inverse is also regular. S is regular, so its inverse is also regular. And the inverse of S inverse is S itself. These are things we already know. We have this R of T is equal to R of S inverse ST S inverse S, which is also equal to R of S inverse ST S inverse S inverse inverse equal to 0. What have we used here? We have used here just simply the fact that if you take the conjugate, because this looks like a conjugate, recall what we mean by conjugate from group theory. Although here, the form of this product is like a conjugate. In that sense, I am saying it's a conjugate. So we have proved that if T is any linear operator, then its conjugate by a regular operator satisfies a polynomial that T already satisfies. And we now have this. You see, now our operator is STS inverse. In place of T, we have that now. And this is satisfying the polynomial R. So if we take the conjugate of this operator by what? By which regular operator? S inverse. Then the conjugate looks like this: S inverse times the operator times the inverse of S inverse. That should also be equal to 0. However, that turns out to be equal to nothing but t. Okay, so R of t is equal to 0. But then we are getting a non-trivial polynomial R which t satisfies, but at the same time its degree is less than the degree of px. But this violates the fact that px is the minimal polynomial for t, and as such by definition should have the smallest possible degree for any non-trivial polynomial that annihilates t. So this contradicts the fact that px is the minimal polynomial for t, and that is why our supposition must be wrong. Minimal polynomial of t. So I said I won't write a formal proof, but I ended up writing many things. But anyway, we have got the idea. That's what matters. Supposition is wrong. That means no non-trivial polynomial whose degree is less than the degree of px can annihilate t, and that is why p not only annihilates STS inverse, STS inverse, that's the operator now, but it is in fact the polynomial having the minimum possible degree to do so. So p of x is the minimal polynomial of STS inverse as well. And that is the proof. Let us now define something which we have already talked about while discussing one of the properties of characteristic roots. You already know that thing as a characteristic vector or an eigenvector belonging to an eigenvalue or a characteristic root. So now we are going to define that properly. Recall that our original definition of a characteristic root does not involve any vectors. It is about an operator being singular. But later on we also saw that it is equivalent to having that non-zero vector there. So now we are going to make that definition. And that definition is this. Let T be an operator on V and lambda this be a characteristic root according to how we have decided to minimize our writing labor. I am again writing ch dot, that means characteristic. Okay, characteristic root of T, a vector v not equal to 0 in V is called a characteristic vector or an eigenvector, and that term we are not going to use here in this text, is called a characteristic vector of T belonging to the characteristic root lambda if Vt is equal to lambda V. Okay, so existence of such a V for each characteristic root lambda has already been established. And now we are going to ask what possible relation can we have among characteristic vectors belonging to different characteristic roots for the same operator T. We will see that such characteristic vectors form a linearly independent set. So that is our next result. It is theorem. Let these k distinct scalars in Fb distinct characteristic roots of the operator T on V. Okay, if an equal number of vectors we take, if this in V are characteristic vectors of T belonging to the characteristic roots, these lambdas, respectively, then they must be linearly independent. They cannot depend on each other linearly. They must be linearly independent. And from this result, we are going to derive some more facts about characteristic roots themselves, especially how many characteristic roots an operator can have. Something about that will come out as a consequence of this result. Respectively, then these are linearly independent over F. So let's see the proof. The proof is by contradiction. Suppose that our vectors are linearly dependent over F, and that means that some non-trivial linear combination of these vectors with coefficients from F, of course, is equal to 0. Then alpha k Vk is equal to 0 for some scalars in F not all 0, not all equal to the 0 scalar, 0 field element. That's what we mean by a list of finitely many vectors being dependent, linearly dependent. Now there may actually be many such relations where, say, taking different sets of scalars, where in each such relation at least one scalar is, at least one coefficient is non-zero, showing that this list of vectors is dependent. But among all such relations, there will be at least one relation which has as few non-zero coefficients as possible. So we are now going to consider one such relation. And this fact itself is a consequence of the well-ordering principle. Actually, I should have started the proof by mentioning something else I forgot. Let me mention it now itself. In the beginning of the proof, we assume the number of vectors to be greater than 1. Do you see why the case k equal to 1 is trivial? I mean, if k is equal to 1, if there is only one characteristic value to, a characteristic root to begin with, and only one characteristic vector, then that vector itself forms a linearly independent set. Why? That is because a characteristic vector by definition is non-zero, and a single non-zero vector in any vector space forms a singleton linearly independent set. That we already know. That is why the case k equal to 1 is trivial, and so we assume k to be greater than 1. Okay, we are going to need this actually. Let us now consider that smallest possible relation. Among all such relations, there is one having as few non-zero coefficients that means scalars, as few non-zero alphas as possible. And after renumbering the vectors, if you need to do so, let such a relation be this: beta 1 v1 plus beta 2 v2 and so on plus beta j vj. I mean, we don't really know whether in this relation all the alphas are going to be non-zero. Maybe this itself is a smallest possible, smallest possible in the sense having as few non-zero alphas as possible. Maybe the situation is such that actually all the alphas here, k number of alphas, need to be non-zero. If you have one of them 0, then you do not get 0. But in general, this j that you see here is going to be less than or equal to k. And this is a relation, again this is 0 of course, which has all its betas, all the coefficients non-zero, But you cannot have another such relation where again all the coefficients are non-zero and where the number of terms is less than j. In that sense, it is having as few terms as possible, having non-zero coefficients. And here all the coefficients are non-zero, where these are all non-zero. Okay. Now what will happen if we apply t on both sides of this relation? Beta j vj t will be equal to 0 t. So let's carry out the calculation on that side. Because t is a linear operator, t will get inside, and also it will get inside. I mean, ultimately you are going to apply t on each vi. The betas will stay outside, and we are going to get something like this: beta 1 v1 t plus beta 2 v2 t, and so on, beta j vj t, and 0 t of course is equal to 0. Now these are all characteristic vectors corresponding to, I mean, belonging to those characteristic values lambda I. So v1 t, for example, is going to be lambda 1 v1 vj t will be lambda j v j. This is equal to 0. Now note that you have this relation, and at the same time you also now have this relation. In this relation you do not have any lambdas. Here you have lambdas. Now what we are going to do, we are going to multiply both sides of this relation by lambda 1 and subtract from that multiple this thing. Or we can do something else also. Instead of doing that, I mean, it's your choice. We can subtract from this relation. I think this is what the author has done, if I am remembering correctly. From this relation we are subtracting lambda 1 times this relation. What will then we get? Beta 1 lambda 1 v1 minus beta 1 lambda 1 v1, that will vanish, but the others will be there. From the above two relations, you know which relations I am talking about. If you want, you can give numbers here. Say this is 1, this is 2. 2 minus lambda 1 times 1. We have this. So if we actually do that, what are we going to get? Here the second term will be beta 2 lambda 2 v2. From that we will be subtracting beta 2 lambda 1 v2, and that will give us this lambda 2 minus lambda 1 times beta 2 v2. Then the next term will be lambda 3 minus lambda 1 times beta 3 v3. Instead of writing that, we just write like this, and finally we will have lambda j minus lambda 1 times beta j vj. is equal to 0. Okay. Now you may ask, what if j itself is equal to 1? Then here actually we do not have anything. If that is the case, what if we have only beta 1 v1 is equal to 0? But you cannot have. Do you know why? You see, v1 already is non-zero. Now beta 1 also is non-zero, then this product cannot be equal to 0. If it was the case that this is the only term in this sum and that is equal to 0 and beta 1 is non-zero, then v1 is it must be 0, because you can then multiply on both sides by the scalar beta 1 inverse. That will prove, using the elementary axioms of vector space, that v1 is equal to 0, but v1 is non-zero. So that thing we won't have. That means j has to be greater than 1. And in fact, this is why we chose k to be greater than 1. So you now have this. Now notice that here something has happened. Since the lambda i's are all distinct, so lambda I minus lambda 1 is not equal to 0. Why? Because by I, of course, I mean any index that you see here, starting from 2 and ending at j. That type of values I is taking. So lambda I is different from lambda 1. So that's why these are non-zero. But at the same time, all these beta i's are also non-zero. And we are in a field which is an integral domain, so their product is also going to be non-zero. For these values of I. So lambda I minus lambda 1 times beta I is also not equal to 0 for these values of I. But then you have got one such relation involving the vi's again, but where the number of non-zero coefficients is less than that smallest relation. That is a contradiction. This contradicts the choice of the, or we can write like this contradicts the minimal nature of the original relation, that is this one. And that is why something has gone wrong. Nothing has gone wrong in our argument. The only thing that is wrong is the supposition. In the beginning itself, we supposed that the vectors vi form a linearly dependent set. So our supposition is wrong, and that's why, of course, you can complete this proof by writing the final line. And that's why the vectors vi form a linearly independent set. They cannot be dependent. That completes the proof. Now this result has a consequence. That consequence is this corollary. Corollary 1. Let T be a linear operator on V and the dimension of V over F be some n. Then T can have at most n characteristic roots in the field F. At most n distinct, yes, at most n distinct. At most n means at most n distinct. At most n distinct characteristic roots in F. Do you remember that the fact that any characteristic root is also a root of the minimal polynomial? Using that fact, we concluded back then that any linear operator has finitely many characteristic roots, because the minimal polynomial can have degree at most n square, where n is the dimension of the underlying vector space. Back then we concluded that the number of characteristic roots can be at most n square, but here we are seeing a much better result, that there can be at most n distinct characteristic roots, which is equal to the number of dimension, which is equal to the dimension of the vector space. How is it a corollary to this? It's almost immediate. Do I have to write a proof? Let me just tell you the idea. In this theorem, what you have seen, that if you consider characteristic vectors belonging to different characteristic roots, then they form a linearly independent set. Now, if you have more than n distinct characteristic roots of the operator T, then corresponding to each one of them you will have at least one characteristic vector, and those characteristic vectors are going to give you a linearly independent set having more than n elements. Is that possible? That is not possible, because in an n-dimensional space the number of linearly independent vectors can be at most n, not more than that. And that's how the number of characteristic vectors which can be linearly independent is bound by the dimension. So if you go back to the characteristic roots, it means that there can be at most n distinct characteristic roots, not more than that. Maybe actually the number of distinct characteristic roots is less than n, but never more than n. So that is the proof actually. There is no need to write this separately. And there is a second corollary. Let T be a linear operator on V and the dimension of V over F be n. If T has exactly n distinct characteristic roots in F, then the space V has a basis over f which consists of characteristic vectors of T. Now in this case, that is the general case. In this case, T has actually n distinct characteristic roots. So that means it's an extreme case. Here we have as many characteristic roots which are distinct as we possibly can. Then the claim is that V has a basis over F which consists of characteristic vectors of T. How? Here also the proof is almost immediate. You first consider the characteristic roots of T, and there are n distinct such roots. So let those roots be. So this is the main idea of the proof. Let this be the distinct characteristic roots. Corresponding to each characteristic root, there is at least one characteristic vector. And let those corresponding characteristic vectors be this. Then, by that previous theorem, these vectors form a linearly independent set in V. Now, what is the dimension of V? N. And how many vectors we have in this set? N. And the set is linearly independent. So this set must form a basis for this vector space. So that's how you have a basis of V over F whose elements are characteristic vectors. That's it. Now in this very special case, it turns out that I'm going to say something in advance. Each linear operator has associated with it a matrix. That matrix, it can be formed, can be associated to a linear operator provided we first fix a basis for the underlying space. If you fix such a basis for such a special operator, then the matrix that can be written that corresponds to that operator has a very nice and simple form. And this idea is going to drive our study forward. How we can express a given operator by a matrix and how simply we can do that. Does there exist a basis of the underlying space corresponding to which the matrix of the operator assumes some particularly simple form? This line of thought is going to be used in whatever comes next in linear algebra. And that's where this section ends actually. After this we have exercises which we will solve in the community section. And that's just it for tonight as well. So see you in the next upload. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.